In this video, we're going to talk about the second way that you can multiply two vectors. That's with the cross product. So let's say we want to take the cross product of vector v1 and v2. So we want to do v1 cross v2. Well, first of all, just like we talked about with the dot product, the symbol we put for the multiplication of these two vectors matters. It doesn't matter in the case of scalar multiplication. We could say a times b like this, or a times b like this, or this. All of these terms mean the same thing. We're multiplying the scalars a and b. And the reason for this flexibility is that there's only one type of scalar multiplication. However, because there's two ways that you can multiply vectors, you aren't allowed to just arbitrarily put a multiplication symbol between two vectors. Because if we did something like this, for example, well, okay, what type of multiplication is this? Is this the dot product or the cross product? So you need to specify, like shown here, that this is, we're crossing v1 and v2. All right, now, why would we cross two vectors? What are the applications of crossing vectors? Well, one reason is you can use the cross product to determine a direction that's perpendicular to the plane that contains two vectors or two line of action directions. Now, this is different from the perpendicular vector that we found using the dot product. In that case, we were using the dot product to find the component of v1 that's perpendicular to the line of action of v2, or the component of v2 that's perpendicular to the line of action of v1. So if this angle theta between the vectors is an acute angle, then the projection line of v1 onto the line of action of v2, here's this perpendicular projection. Okay, and so here is the component of v1 that's perpendicular to the line of action of v2. It's perpendicular. You could find this vector using the dot product. Or again, you could go the other way, the component of v2 that's perpendicular to the line of action of v1. However, the perpendicular direction that is being referred to here with the cross product is, so the v1 and v2, either as vectors or if these were directions, let's say, are contained within a plane. There's a unique plane that contains both of these vectors and the angle between them. And the direction that you can find using the cross product is the direction that's perpendicular to this plane, normal to this plane, either above or below the plane. So this direction or this direction you can find using the cross product. Also, based on the information you have, you could use the cross product to find the angle made between the line of action of two vectors or two directions, but that's more commonly done using the dot product. But if you had limited information, or maybe you had only some cross product information, you could use the cross product to get this angle. Another use of the cross product is based on the way it's defined, the design, the definition of the cross product. The cross product is well suited for finding vectors associated with rotational phenomena, anything related to rotations, torques, moments, etc. Because we know that when it comes to spatial vectors, there's spatial vectors that are related to linear changes in space, like velocity, momentum, acceleration. But there's also spatial vectors related to angular changes in space. And in those cases, the vector itself, the direction of the vector, corresponds to the axis of rotation. Now, if you think about it, when it comes to the axis of rotation of some sort of rotational phenomena, that axis is going to be perpendicular to the plane containing the actual physical phenomena that's taking place to cause the rotation. For example, if V2 was a force vector and V1 was a wrench, like an actual wrench you would get out of your tool shed, this was the length of the wrench, then you could think about, so if this is the length of the wrench and here's the bolt the wrench is fastened to. So this force, V2, isn't necessarily perpendicular to this axis of the wrench here. So you can see this isn't a perpendicular angle here. But you don't have to apply a force on a wrench that's perpendicular to the wrench. You probably should, but you don't have to. But if we wanted to calculate a torque vector that this force and wrench combination are making on the bolt, what we would want to do is we want to have some operation that would either take the component of the force that's perpendicular to this line here, or you could find the line that passes through the bolt and is perpendicular to the line of action of the force. Either way, so this line here, or you could say what's the component of the force that's perpendicular to the wrench axis, either way, and we want to multiply this perpendicular force component and this distance, or the force itself and this distance. Either way would work. And that would be the magnitude of the torque. But then we would also want the direction of the torque, the axis of rotation, to be perpendicular to the plane that contains this the wrench axis and the force line of action. Right? This can be oriented in any way in 3D space. However it's oriented, we want that axis of rotation, the magnitude of that torque vector, to be perpendicular to the plane that contains these two lines. And that's exactly what the cross product does. And so with that, you can see when it comes to mechanics, forces, motions, accelerations, in particular mechanics related to angular accelerations, torques, moments, any angular motion, tendency of forces to cause rotation, the cross product is made for doing these types of calculations. But okay, so how do you calculate the cross product? And how does it all work? All right, well, first of all, remember that the cross product, the output of the cross product is going to be a vector, as opposed to with the dot product, the output is a scalar. That's why the dot product is also referred to as the scalar product, whereas the cross product is referred to as the vector product. Okay, so V1 cross V2 is equal to, so just like with the dot product, we start off with the magnitude of V1 times the magnitude of V2. And these are scalars, so we don't have to put a multiplication symbol. We can put whatever we want. Okay, now instead of this times cosine theta, we're going to say times sine theta. Theta being the angle made between the lines of action of the two vectors. Where, just like with the dot product, we can bring the two vectors together, tail to tail, to visualize the cross product, but even if the vectors were separated, we can still, like permanently separated, they're fixed in their places, we can still interpret the cross product from that perspective. So you extend the lines of action. This actually happens to extend right to the tail of V1. Let me try and make this more general. Okay, there is theta. All right, but now we're not done with this formula yet. We can't be, because this is a scalar. This is the dot product. Just instead of with a cosine theta, there's a sine of theta. So we'll finish this formula off in a second. But what this is here, this is the magnitude of the vector that's going to be the output of V1 cross V2. Okay, and then just like with the dot product, theta is going to be the acute angle between the lines of action of the two vectors. The acute angle. So you don't go, theta is anything from, so it's less than or equal to 180 degrees or pi and greater than or equal to 0 degrees. If you went to 181 degrees, well, that would just be 179 degrees then. If you went to -1 degree, that would just be 1 degree. Okay, now, but something to notice here, though, is that, so we know that cosine theta, when theta is between 0 and 90, if it's an acute angle, cosine theta is positive. If it's if it's an obtuse angle between 90 and 180, cosine theta is negative. However, sine theta, at least between 0 and 180 in the first and second quadrants, is always positive. So that's interesting. This is a magnitude. This is a magnitude. So magnitudes are always positive, the magnitudes of a vector. Sine theta in this case is always positive. So this is always positive. Okay, now we can also notice that just like the dot product, when it comes to calculating this value, we're not going to need to convert the vectors to rectangular if we don't want to. Because the magnitude of V1, the magnitude of V2, yes, to calculate those magnitudes and use the traditional magnitude formula, you'll need to be in rectangular, but just the magnitudes themselves, that's just a length of a vector. It doesn't matter what coordinate system you're in, it's just the length of the vector. So this is independent of coordinate system, this is independent of coordinate system, and so is theta. Theta is, the angle between the vectors is the same no matter what coordinate system you're in. So all of this is independent of coordinate system. Okay. However, just like with the dot product, there's going to be another way to calculate the cross product that involves matrices. And in that case, you'll need to be in rectangular. Okay. But we're not done with this formula because this is just a scalar and the output of the cross product is a vector. So to finish this, you take this scalar and you multiply it by a unit vector that is normal to the plane containing V1 and V2. Now, we're multiplying a scalar by a vector, so scalar multiplication of a vector, we don't need to put any sign. It doesn't matter what the sign is. So we could write 3 V1. This is fine. Scalar multiplication by a vector. So we'll just put no multiplication symbol here. Okay, and that is the cross product. Now it's a vector. Once you multiply this scalar by this vector, now it's a vector. This unit vector that's normal to the plane containing V1 and V2 is going to be scaled up by this magnitude here, which is always positive. So there's no way this is going to be negative and flip this direction. So the question is then, how do we know if this direction is going to be above or below the plane that contains the two vectors? Because we can get this magnitude. We've got the magnitude, right? So we get that magnitude. Now we think about the plane that contains these two vectors. That's fine. But what direction is u hat in? This direction or this direction? Okay, well, we figure this out using the right hand or left hand rule, depending on whether or not we're using a right-handed or left-handed coordinate system. So let's say we're using a right-handed coordinate system. Then to figure out the direction of the normal vector, you bring the tails of the two vectors together. Now you might be saying, well, wait a minute, what if the two vectors are fixed vectors and we can't bring the tails together? Just bring them together anyway for the purposes of getting the direction and then put them back. It's like from the perspective of multiplying scalars. If I had a pan over here with a certain temperature and a pan over here with a certain temperature, but for some reason I wanted to multiply those temperatures, that's up to me. If I want to multiply two temperatures, this is T1, T2, but I want to multiply the temperatures. Well, then I can bring those two scalars together. If T1 is 50 degrees Fahrenheit and this is 75 degrees Fahrenheit or something, I can bring those. I mean, I can do whatever I want as far as doing the whole operation, right? I'm just doing the multiplication process. So, okay, now, so the tails are together. And now if we're doing V1 cross V2, V1 is first, then you take your right hand and put the palm of your right hand along V1 so that the curl of the fingers are facing towards V2. So like that, curl of the fingers facing towards V2, then just push V1 to V2. And what direction is the thumb facing? Well, it's facing into the page, or, over here. So that's going to be V1 cross V2. If you in a left-handed coordinate system, you would do this with your left hand, in which case the vector would be in the other direction. Okay, if you were doing V2 cross V1, then you would put the palm of the right hand on V2, curl the fingers facing towards V1, push V2 to V1. Which direction is the thumb facing? It would be in this direction. Okay, and that is how you get the direction of the normal vector. There's one of two possible directions. So once you have that direction, you can just go ahead and bring the vectors back into their spots. Or maybe they naturally do have their tails fixed wherever they are. Okay, now what you can notice about this process is that if we were in a right-handed coordinate system, let's say, well, with the right hand just now, when we did V1 cross V2, the vector was below the plane. The cross product vector was below the plane containing V1 and V2. But when we did V2 cross V1 with the right hand, this vector was above the plane. And so that's why the cross product, unlike the dot product, is not commutative. It's close, but technically not, because the difference, it's close because the difference is V2 cross V1. You're going to get the exact same magnitude because this is commutative. You could switch these and sine theta, the order of this, it doesn't matter. So the magnitude is the same, but the only difference is you're just going to flip the sense of U hat n. You can multiply this by -1. That's the only difference. But still, that's a difference. So V2 cross V1 is equal to minus V1 cross V2. You're just flipping the vector. Okay, but now how do we calculate this vector? How do we get, we can see how we could get the magnitude. That's fine, but how do we get the vector in that normal direction? Well, with analytic geometry, from the three-dimensional perspective, which we learned at the start of Calculus 3, we could get the equation of a line in a plane and then use our understanding of perpendicular slopes to get a perpendicular line to that plane. So if we understand analytical geometry, we can do this. However, a quicker way is to use the matrix method for calculating the cross product. So how does the matrix method work? Okay, well, again, with any of these matrix methods, you want to convert the vector spaces of the vectors to rectangular. So, for example, let's say we were working in a cylindrical coordinate system, in which case we would have the vector spaces of all the vectors be in cylindrical with the axes of the main coordinate system so that the directions of the vector spaces and the main coordinate system line up. Well, then if we were doing some operation on a vector or between vectors, in particular when this operation is going to involve the vector matrices, then we want to convert the vector spaces of the vectors to rectangular. Do the operation, then convert everything back to cylindrical. Okay, so we're in rectangular here. Now we want to calculate the cross product, V1 cross V2. And so, yeah, just note that anytime you're doing vector operations, those operations are based on the vector space coordinates, not the main coordinate system. Adding, subtracting vectors, scaling vectors, the dot product, etc. That's based on the vector space coordinates of the one vector or the pair of vectors that you're doing the operations with. Okay, so we've got the two vectors in rectangular. What's the matrix method for calculating the cross product? Okay, now just also note again, to do the cross product of these vectors, it's not like we have to have the tails aligned. We could take the cross product of any vectors in any circumstance. Okay, so let's leave it like this. What is V1 cross V2? Okay, if V1 is equal to V1x, V1y, V1z in rectangular, right? And V2 is equal to V2x, V2y, V2z. Then V1 cross V2 is equal to the determinant of a 3x3 matrix where the first row is I hat, j hat, k hat. The second row are the components of the first vector, and the third row are the components of the second vector. Okay, so the determinant, if you look up the formula for a 3x3 matrix determinant, it's going to be, so we start here with I hat, we cross out this column and this row. So now what's the determinant of this 2x2 matrix? That's V1y, V2z minus V1z, V2y. Okay, now all of this times I hat. Okay, now the next term we put a minus, and then we come to j hat, cross out this row in this column, and what's the determinant of this 2x2 matrix? V1x, V2z minus V1z, V2x. J hat. Okay, now plus, and we come to the third to k hat, cross out this row, this column, the determinant of this matrix. So that's V1x, V2y minus V1y, V2x, k hat. And that's it. You've got your vector components here. You just plug them in to this formula. And the result is going to be some vector, something I hat, something j hat, something k hat. It's going to be this vector in Cartesian components. And that vector, if you plot that vector in the case of, so in this case, if the main coordinate system was in cylindrical, then what we would do is we would bring these vectors back to cylindrical, convert this vector to cylindrical, and plot the vector. Or if we were already in rectangular, we would just go ahead and plot this vector in rectangular. And the result is that this vector is going to be perpendicular to the plane containing V1 and V2. This doesn't matter what coordinate system we're in. This is going to be the result. It's going to be perpendicular to the plane containing V1 and V2. So there's V1 and V2. It would be, here's some plane, perpendicular to this plane. And in this case, right-hand rule, it would be into the page, like below the plane. That's going to be the direction. And the magnitude is going to be this. Okay, cool. Now, there is another way that you can calculate the cross product vector without having to memorize this determinant formula, but this isn't so bad. And I'll go through this other method in the next video. I'll do a cross product example with actual numbers and show that method in addition to using the determinant method as well. Okay, now, note that for all of the operations between vectors that we've talked about, between vectors, so addition, subtraction, the dot product, the restriction was that the vectors had to be the same dimension. You couldn't dot a 4-dimensional vector with a 3-dimensional vector. You can't add a 4-dimensional vector and a 3-dimensional vector. But you could add a 10-dimensional vector to a 10-dimensional vector. You could take the dot product of two 20-dimensional vectors. Okay, the cross product is different in that you can only cross two 3-dimensional vectors. There's no cross product of two 2-dimensional vectors. There's no cross product of two 5-dimensional vectors. You have to have two 3-dimensional vectors to do the cross product. Now, but if we make sure we understand exactly what the cross product means from a geometrical standpoint in 3 dimensions, then we can abstractly think about the idea of a cross product with 2 4-dimensional vectors or 5-dimensional vectors. And actually, in 2 dimensions, that there would be a parallel to the cross product. However, when you officially say you're going to be crossing 2 vectors, and you use the cross notation, then these 2 vectors are strictly going to be 3-dimensional vectors. But okay, let's talk about what exactly is geometrically going on with the cross product. Okay, so V1 cross V2. Let's go ahead and bring the tails together, even though we don't have to. We could just extend the lines of action. Okay. So the magnitude of the cross product is extremely similar to the dot product. The only difference being this is sine of theta instead of cosine of theta. Okay, so what that means is that, what is the magnitude of V2 times sine of theta? Well, if we think about the projection of V2 onto the line of action of V1, let's say this theta is acute, so we'll be coming, inside the vector V1 onto the vector V1 here. Okay. Well, this is the projection of V2 onto V1, the scalar magnitude. Okay, but since this is sine of theta instead of cosine of theta, then V2 sine of theta is this distance. The perpendicular sort of moment arm of V2 relative to the line of action of V1. Okay, and so that's V2 sine theta. So what the magnitude then is, this entire group of terms here, is this distance times the magnitude of V1. So instead of this distance times the magnitude of V1, it's this distance times the magnitude of V1. Okay, but just like with the dot product, there's also that duality in the sense that we could put the magnitude of V1, we could think about this as the magnitude of V1 sine of theta times the magnitude of V2. So we can think about the projection of V1 onto the line of action of V2, which would be this distance. However, since it's sine theta, it's this distance times the magnitude of V2. It's the same number in either case. Okay, but however, with the cross product, we're not just finishing with a scalar. We're taking that scalar and using it to scale a unit vector that's normal to the plane containing these 2 vectors, so that the result we get is a vector, with whether or not that vector is above or below the plane containing the 2 vectors is based on the right-hand rule or the left-hand rule. Okay, but it's important to note that it's not like these vectors you have to be at the same spot. You can cross vectors in whatever circumstance you see fit. So if we were crossing V1 and V2 here, maybe if we could look at a downward view of these 2 vectors, maybe this line of action doesn't even intersect the line of action of V1. It just looks like it does from the side. Well, that's fine. It doesn't matter. This is still the angle theta. And we would think about, if we looked at it from the perspective of the moment, kind of that perpendicular distance of the V2 on the line of action of V1, then we would just think about a line here parallel to V1. And there's the projection. So V1 cross V2 would be this distance times this distance. That would be the length or the magnitude of a vector that is pointing below the plane containing the 2 vectors. And that would be it. V1 cross V2. You could take this vector and do whatever you want with it.